Okay, so yes, it will be a more informal talk, and wow, this is loud. Turn on the tracker. Okay, and I take this a bit further away. So for this talk, I will basically go through some details from the talk yesterday, and I also added some searches. It's way too much material, so it's basically up to you to tell me where you want to see more and where I go through it a bit faster. Before I come to the actual talk, yesterday there was the question, roughly speaking, when will we see the cubic standard model Higgs coupling and at which machine? So I was yesterday evening looking a bit through the literature to find slides. And I found two recent studies. One study, this is a large group of mainly theorists who did fits for the high luminosity LHC, and so for the di-Higgs you have many different combinations of decay channels, so you want to do a fit to this, and here this is parameterized in terms of the ratio of the basically the bound on the triple Higgs coupling over the standard model value. This is the kappa lambda here, so the standard model is the dashed line, and here the lines you see are the reported current limits from CMS and Atlas, and the projection this collaboration got for one experiment at LHC with the full run 2 data. The analysis is not out yet. Both experiments with the run 2 data, and here the projection for the run 3 data, i.e. not the high luminosity LHC yet, and you see that this is still half an order of magnitude away from being measured at run 3. And another big study, this is basically many people who do Higgs fit, and also by the many people who do future collider projections. This is just a table I took from there, and here in the first column you see the projection the different experiments give for the precision they reach on the or they think they can reach on the triple Higgs coupling. So for the high luminosity LHC, you get about 50% error, i.e. this will not be a discovery yet. At the high energy LHC, the projection is 10 to 20%, and then if you go into the E plus E minus machines, then there you can reach higher precision.
The high energy LHC is the one with 57 dB.
I think the high energy LHC projection here is the 27 TeV projection.
So FCC 240, or why there is no number for FCC?
If you go to E plus E minus machines and you want to produce 2 Higgses, you need naively 250 GeV already, but actually I think you produce this with an additional electroweak gauge bosons. So basically those center of mass energies are too small in order to give you any sensible di-Higgs signal. This is a huge paper, and they also did indirect or fits to indirect information you can get on the triple Higgs from measuring, doing precision measurements on the single Higgs. I just looked at the paper yesterday evening. Oh, by the way, if you go to the slides, all the references are linked. So if you want to look at those 2 papers more, just look at it, but those are big reports which do the projections in all details.
So is 5-4 coupling or 5-squared coupling?
So the coupling here they take is the coefficient of the triple Higgs term.
So the 5-4 term, because Higgs has some expectation value, generates a cubic term.
Exactly.
That's the term you're...
Yes.
And what's the prediction for it? There's no model that tells you what it should be, or is there
Um,
Indirectly.
in the standard model,
Yeah, so there are two. So you have phi 0 and you have the coefficient in front.
exactly. So everything is fixed. We know the mass and the vacuum expectation value.
Can you go back one slide?
Yes.
So this is a prediction.
So what they do here is they say we have the standard model value of this triple Higgs interaction, and we put a bound on basically how close we can get to this value. So this dashed line is the standard model, and if this coupling would be factor 10 times larger, then you would get a different value in the model and also a different bound.
Can you just write down the Higgs we're going to pursue?
Okay, so you basically
Just the self-coupling, nothing else.
just the self-coupling. So you want to go to the mass term, and then the lambda phi to the fourth. Sorry, phi squared, and now basically from this term,
So what's known about lambda? That's what I meant. So we know the mass, but we don't. What is
we know m Higgs, and we know the vacuum expectation value. And we can map this one-to-one to our parameter mu and the parameter lambda.
Comes from the
The vacuum expectation value we know, for example, from the W mass, the Z mass, and the coupling of the measurement of the weak couplings.
So the precision of lambda is the same as the precision of mu, or is it better, or is it worse, or is it linear in mu, or I'm just trying to understand how much we can predict from the standard model.
If we assume that the standard model is the right model, we can predict everything.
No, but what's the theoretical uncertainty? There's some theoretical uncertainty in mass Higgs, right? We know it's up to a certain.
So, okay. V is something you measure actually most precisely in muon decay. And here the theoretical error is extremely small.
So it depends on MH, right?
No, this measurement is completely independent of MH. All which goes in there is the vacuum expectation value of the Higgs. I'm measuring not the Higgs potential when I measure V. I use the electroweak part of the Lagrangian.
This precision doesn't even need the mass of the Higgs.
This is not a precision. So this is saying this is saying we can measure, or the production cross-section for two Higgses, assuming the standard model value is precisely the point in the dashed line here. So it's of the order of 60 picobar. So that's the value of the standard model. Now, the way they parameterize this is they are saying, well, if I would have a beyond standard model contribution, which is only enhancing the triple Higgs coupling, then I could have a different value for the triple Higgs coupling, and it could be larger or smaller than the standard model value. And this is what this band is giving you. And what you have here is the measurement of or the current bound from the experiments.
You see, from the definition of kappa there, the standard model condition is the denominator. Right? He's asking the certainty on lambda, so just write the relation between the Higgs mass and lambda, and then you know the uncertainty on the Higgs mass and the uncertainty in lambda. That's all. Yeah, but that's dominated by experimental uncertainty. That's what I'm saying.
That's what I'm trying to ask.
That's what
Okay,
I'm saying.
so
Just write the mass of the Higgs in terms of lambda and V.
don't even need to do this because this is determined extremely precisely. So all the error on the triple Higgs coupling comes from the precision of the Higgs mass. This is below, well below a GeV by now, i.e. it's below percent level. Yes.
So you need 1% precision on this in order to get something new, is that what you're saying?
No, what I'm saying here is that currently the measurements which look for this process are only sensitive to about 6 times the coupling. Right? This value here is about 6 times as large as this value. When this line eventually goes beyond, below this value, then I have experimental sensitivity for the standard model value.
This prediction also depends on the top Yukawa coupling.
This prediction also depends on the top Yukawa coupling. Yes, there are additional things in there because the di-Higgs has the top triangle in, and this is probably the dominant contribution if you use this parametrization. They put so here you have the theory band in there so this is this reddish area is the theory error. And this
also the cancellation depends a lot on the Yukawa of the top, right? Because one
yes.
top Yukawa square.
So this is what in this parameterization is must be the dominant factor for this error band. This is going to rule out certain composite Higgs models, and those are, or this is one way of ruling the models out if the value of the triple Higgs is modified in such a way that it gets here that the coupling goes negative, or on the other side, if the coupling gets more than 10 times as large as the standard model, you can use this in order to rule out models with modified Higgs couplings.
Basically, at the end of round 3, we are not. So we measure across section. Suppose the value is standard model value for lambda, then we will be able to measure only cross section that is by 10 times.
Yes.
Only if this is like modified, if it is 10 times larger, this number for some reason, then we are able to measure.
So then we can use this in order to rule out some models. From the point of the standard model, the aim is to really go down here and go below this point. And so this is the projection for 300 inverse femtobarn. This is not the full high luminosity. If you do, so there are lots of assumptions also in those things about whether you are systematics dominated or whether you are statistics dominated. This is statistics dominated. So as a very naive estimate, if I go from 300 inverse femtobarn to 3 attobarn, I gain a factor of 10. If I am here statistics dominated, and if I'm at 3 inverse attobarn also statistics dominated, then increase of a factor of 10 gives me an increase on this line of about square root factor of 10, i.e. about factor 3. So this would tell you that with high luminosity, this is roughly a factor of 3 here. So with high luminosity, you get into the rough regime. And the values quoted here from the respective experiments, so they are just listed here. This says that the projection for the high luminosity is basically measuring it with a 1 sigma error of -50 to +60%. So that means that you're getting into the area where you can start seeing the triple Higgs coupling. But if you want to ask the statistical question, do we discover the di-Higgs channel for this? This is too too little, because this is a 1 sigma error bar. But in detail, it's a completely different test, because then you want to make a hypothesis test.
The experimental lines in the previous plot, they are upper bounds, no?
Those are upper bounds, yes.
Upper bounds, eh?
Yes.
So these are cross-section.
Yeah, an upper bound.
Well, yeah, those are measured cross.
They're theoretical predictions.
No. Those are experimental upper bounds on the Dye-Higgs cross-section,
The dashed ones.
the dashed ones. And
They don't have they already have an analysis of rim 3. No, that's the first.
so the blue line and the red line is the CMS and the Atlas result. The dashed lines are the projections of the collaboration here, which is a large group of mainly theorists, which is saying how much sensitivity could you get, assuming that you don't see any excesses. So this is giving you those 2 lines, and then they extrapolated to how much can you see with 300 inverse femtobarn. Okay, so this was a much longer excursion than I was hoping, and this is not my work, and what I told you now was basically what I was reading up yesterday night, so I apologize to the authors of those papers for so poorly representing their work. But I think it's an interesting and important question, so at least you have the references and we have some idea of the bounds. So let me come to the composite Higgs models, and the lineup is basically the same lineup as for yesterday, but I put in more details on the theory part, i.e. on the underlying models and how we calculate bounds for neutral pseudo-Nambu Goldstone bosons. And I also put in several more experimental analyses we have been performing or we are performing in the moment. And now I will for sure not be able to go through all those things. So I don't know, are you more interested in the theory part or more interested in the analysis? Or I start with the theory part, I go quickly, and you say stop whenever you have a question. So this I showed you yesterday, just as a recap in case somebody was not around. Composite Higgs models, you want to have a new gauge group which gets strongly coupled at the TeV, and matter content which is charged under this, which confines and gives you bound states and gives you chirosymmetry breaking here. And you want to have in particular the Higgs multiplet as one bound state from the strongly coupled sector. This is strongly motivated by an analogon to QCD basically. And you expect to get your compositeness scale at, or you want to have the compositeness scale at around 1 TeV, pushed by experimental bounds on the Higgs and on electroweak precision. You want to realize the Higgs at 125 GeV. As you will get many strongly coupled resonances which should sit around this scale lambda hypercolor. You want to have top partners in order to generate the top mass, and those ideally are a bit lighter. And depending on if you have additional pseudo-Nambu Goldstone bosons, you would expect those to be also lighter than at least the scale of those few TeVs. Also discussed yesterday, those models have been, or a wish list has been formulated, and those models have been classified. And the wish list is to have no elementary scalars, simple hypercolor group, a Higgs candidate, and a top partner. And the example model I also showed you yesterday. Here is a gauge group of sp2 and C, and you take two types of underlying fermions. One type of underlying fermions gives you a global symmetry group in which you embed electroweak. So here you take 4 fermions in the fundamental, which give you an SU4 symmetry. And the reason why you choose this gauge group and those representations is you want to have some singlet bound state under this gauge group. In this case, it's psi-psi, which breaks this SU4 down to SP4. And in order to get top partners, you also need to embed colors. So you need another set of fermions, which here have an SU6 symmetry. Now, if those condense, and you have them here in the antisymmetric, so if you take 2, you can form singlet chi-chi, and if this condenses, it breaks the SU6 to SO6. And this gives you additional colored Goldstone bosons. You don't necessarily want to have them, but you just get them out of the model. But you needed to choose this representation in order to be able to build bound states of chi's and psi's, which have the right quantum numbers to be paired with the top. So that's the kind of game on how to construct those models. You want to get the Higgs and you want to get the top partners, but along the way you get additional colored and uncolored Goldstone bosons, and you get tops in several representations.
Sorry, in order to get condensation, you need an extra gauge or an extra interaction, right? That becomes strong. These are all global groups.
So those are fermions which are charged under the sp2nc in those representations. And the sp2nc,
right,
we assume to become strongly coupled at around the TeV scale.
Well, these are not global symmetries that we're talking about?
So this is a gauge theory. So this is gauged.
Okay.
Those are the global symmetries I get just out of the number of fermions I have here. And in those global symmetries, a subgroup of this SU4 is gauged, which is precisely my standard model electroweak group. And a subgroup of the SU6 is gauged, which is my SU3 color. So I have to make sure that from the strong or from the high energy point of view, the gauging of those of the standard model subgroup doesn't play a role. Everything is weak. So from the strong coupling point of view, I need to make sure that when this condenses, that the condensate breaks in the right way, that the standard model group is not broken by it. And for example, in the SU3 has to be embedded in the SU6 such that the SU3 is unbroken through the condensation.
How do you guarantee that?
How do you guarantee this? Basically, you have the SU6 and you break it to an SP6, but before you have the breaking, this is basically just singling out one particular direction. So you have the gauge part aligned with this direction automatically. It's also when I write the quantum numbers or when I write the fermions here and I write the SU3 cross SU2 cross U1y quantum numbers, you see that they are already kind of split into different representations here. So this is basically taking into account the alignment.
But this is a dynamical question, right? Whether this condensation breaks or not, condensate breaks or not.
You are saying, do I generate a miss? So the gauging singles out one subspace, and my condensate could or could not break this subspace. So yes, in the end, it's a dynamical question where here you have to have the breaking in such a way that the SU3 is not broken. Typically, if you only have gauging in those models, then you are driven to a point where those things are aligned. Actually, one big task in the composite Higgs models is also with the SU2 cross U1, you will get the vacuums aligned, and if you want to have spontaneous symmetry breaking, you need some other contribution which is pushing you away from this alignment, so you need a slight misalignment. The pure gauging will push you back to this, to the aligned minimum. So the reason why you want to have the top partners and the mixing is to have a second part in the potential which gets you away from it.
I guess the question I want to ask is whether this is a really UV completion that you can trust.
So this is not a complete, or this is not a full UV completion. And the reason it's not a full UV completion is, but I think I'll come to that later, is in this point, we classified the states, but now if I want to bind, or if I want to get a mixing with the of the elementary top with the top partners, I need a coupling which involves the elementary top and those three fermions. So this is a 4-fermion operator. And this 4-fermion operator, we do not generate just out of this field content. So it's not a UV complete theory, it's a UV embedding. You need something at high energy which is generating those 4 Fermi interactions. This needs additional model building, and there are several approaches to this. In the Gergetta paper, this has been done by a Nambu-Iona Lacino model. Giacomo Cacciapaglia is working on several ideas how to get this from UV complete models, but it's not a full UV completion. This is an important point, yes. So with those UV embeddings, again, this is one example, and I flashed the list yesterday, which is a bit hard to read. But just to say, to show you what is listed here, those are the gauge groups which are confining. Those are the representations for the 2 types of fermions in terms of real, symmetric, fundamental, spin. We also have anti-symmetric representations. And here you have the breaking patterns. Basically, those things fall into, in the electroweak sector, you get 3 possible breaking patterns, which is SU4 to SU5 to SO5. You can get SU4 to SP4, and you can get SU4 cross SU4 broken down to SU4 diagonal. And in the QCD sector, you get either breakings SU6 to SO6, SU6 to SP6, and in this model here, you get SU3 cross SU3 to SU3 diagonal. So those are basically the combinations. We numbered through several of the models, but not all of the models. This is basically, you want those models to have a chance to be not conformal, but close to the conformal window. If the models are conformal, you don't get a mass gap. If you are far away from the conformal window, then it is difficult to get a large anomalous dimension for the top partner, which you need also in order to get the top partner, to have a chance to get the top partner lighter than the other bound states. So the models which are numbered through here are, and it is a very difficult question to say whether a model is really inside or outside the conformal window. So those models here are models which have a chance, and there I'm referring to Gabriele Ferretti, to be near the conformal window but outside the conformal window, and this is why we picked those 12. Just from the construction, there would be a few more, but they have typically fermion content which is so large that it's pretty sure that they are in the conformal window.
So conformal means exactly conformal? What does conformal window mean?
It's basically that you get driven to a fixed point because you get very strong running there. So if you have 2 large fermion representations, then basically you don't expect that you get your confinement at a low scale.
I understand data function perturbative, but how do you say anything about confinement?
So basically, if you have a strictly conformal theory, it's not.
Strictly conformal means exactly conformal. I just don't know what the language is. That means it's just if you don't break beta function to 0, is that strictly conformal? I just don't know what you mean by strictly conformal.
I mean that you don't get a running of the beta function. So in that case, your coupling never becomes strong in the IR. You don't develop a mass gap. And those are no good. There is actually a way to make them good, and this can be a very useful model building tool, which is if in those models you have many fermions, but you give a Dirac mass to one or a few of those fermions, then you can induce a beta function. So you can have something which is down to a mass, a Dirac mass term of some of those fermions conformal, can become non-conformal if you integrate out those fermions.
So if you bring in a mass term, then you can make it conformal. What is conformal window?
I should not say too much here because I'm not an expert on it. So this is one of the not requirements, but one of the things in the wish list we have been using in order to, or Gabriele has been using, in order to end up with those models, which is an additional assumption. Then let me come to the, this I also showed you. You get different types of Goldstone bosons. You get those two Goldstone bosons from the U1 factors. You get the colored octet, and depending on which breaking pattern you get not only the Higgs multiplet, but additional electroweakly charged and additional singlets in the electroweak sector, and also additional sets in the colored sector. So here, what I have now is several slides on, if you go to this, just to the singlet case, basically on how to calculate the coefficients for the couplings of the pseudoscalar and of your anomalous eta prime. And I don't know in how much detail you want to see those, so I just try to be quick. The main point is, so we parameterize this just via Goldstone boson matrices, and now in detail, you have really four symmetry groups here. You have the electroweak embedding group, the SU4. You have the group for the strong sectors, for example, SU6. Which is broken down, but you also have the two U1 factors. So really you have the non-abelian groups with 2 decay constants and the U1 factors which also come with 2 decay constants. So then we just take the chiral Lagrangian, but you can have different decay constants for all those 4 groups. And we make some assumptions about the relations of those decay constants. So for example, for the U1 factor as compared to the non-abelian factor, we are assuming that the U1 factor is related to the non-abelian factor by a factor of square root nr, where this is the dimension of the representation. This is something which holds in the large n limit for gauge theories, but which is not an exact relation. So this is one assumption we are putting in. And also to relate the decay constants of the 2 non-abelian groups, we are making another assumption which is called maximal attractive channel approximation. This is also an assumption we are using. In the end, those relations are not exact, but they can be tested on the lattice. So upshot here is we have pNGBs. We can have different decay ratios, and those can be estimated, but cannot be exactly, or the relations are not exact. Now, if you want to get masses for the pseudo-Goldstone bosons, for the pNGBs, the weakly gauging gives mass to the pNGBs, but not to the U1 factors because they are not charged under the electroweak group. Elementary quarks and tops can give you contributions because it's an explicit breaking via the top partner mixing, but they also don't give a contribution to the mass of the U1 singlets because they have the same spurion mass. And then you can give masses to the underlying fermions, which are explicit breakings, and those give you masses to the also to the U1 factors, which are related to the masses or to the mass additions you give to the non-abelian factors.
Can you go to the previous slide?
Yes.
Yeah. So you have R is psi, chi, and pi. Pi A. So what are the pi A's?
Sorry, here the pi A's are the Goldstones you have in the non-abelian breaking, i.e. From the SU4 to SP4 breaking, or from the SU6 to, for example, SO6 breaking.
So they are fundamental fields.
Those are Goldstone bosons.
They were not on the table, no? The big table.
They are on the big table. Wait. If I go here, so here it's actually those Goldstones. From SU4 to SP4 and SU6 to SO6. So it's those Goldstone bosons. This includes the Higgs, and it includes colored. Those pi A's are psi or chi states. And in addition to those pi A's, you also have an U1 factor here for the psi's, and you have a U1 factor for the chi's. So those are two additional Goldstone bosons you get from the model, because your full global symmetry group is SU4 cross U1 broken down to SP4, and it's SU6 cross U1 broken down to SO6. Psi is a constituent, yes.
And
pi is a composite.
And then you consider all of them in the theory, no? You consider a theory of constituents and composite states.
I don't consider a theory of the constituents. What we do is we take those particles and we do model building with those particles, i.e.
No, I was confused because after that you have some, it is exponential when you sum over R.
It's just an index.
Wait a second.
Psi as an index.
Sorry, here?
Yeah. So,
You see, psi and chi are just indexes for pi.
Yes, so I'm labeling the different decay constants according to whether it's the decay constant corresponding to the psi-psi condensate or the chi-chi condensate, or the U1 factor of the psi-psi or the U1 factor of the chi-chi. So that's not... So you get different decay constants. You can determine ratios in principle on the lattice. We use an approximation for what we are doing. You get mass contributions to the Goldstone bosons, but the electroweak gauging and the top partners don't give you mass contributions to the U1 factors. The couplings of the pNGBs to standard model gauge bosons, this is basically because now your pions are constituents, or you have your, let's say you have a chi-chi state. But those through the weak gauging those constituents have standard model quantum numbers. So basically in the same way as for the pions, I can effectively just calculate my anomaly for the gauge bosons. And in this way, I can calculate the anomaly terms for the chi-chi and for the psi-psi condensate. And this calculation is basically exact, so a calculation of anomaly factors. However, for phenomenology, in principle, you have form factor corrections here, which we don't take into account in our phenomenology, so this is another approximation we're making. Couplings to the top. It's a longer story where I'll just give you the summary, unless you really want to go into the details. It's basically, if you want to write down a mass term for the top, then you have to get this from a certain or you have to get this from a combination of, or from the Goldstone boson coupling to the top left, top right. So you can do a spurion analysis. And the same term also gives you couplings in the next term in your expansion of the pseudo-Goldstone bosons to the top partners. So in that way, depending on the spurion charges of your top partner, you can determine the couplings of your pseudo-scalar singlet to TT bar.
So your top partners, they have no mass terms?
My top partners they don't have mass terms, but those are bound states. So those are basically, you could say, baryons. Yeah, I'm careful with the word, so it's 3 fermion bound states of your theory, and you would expect them to be at your cutoff scale.
So you expect them to have a dynamical mass, even if...
Yes.
So why can't you propagate this mass to the top by the mixing you just introduced at the top?
You propagate the... yes.
Your slide you were.
Yes.
That one, so the first line on the top, the Lagrangian on the top of your slide.
Yes.
And if the psi's have masses, then you get some mass for the top from the mixing.
Yes, you do.
Can't you just do that and forget the full fermion interaction?
No, this is the full fermion interaction, because this capital psi is a chi-chi psi state. So that's what I mean, and yeah, this is precisely the point where we don't have a full UV completion, because we do not explain where those mixing terms are coming from. We are assuming that they are there. And so here on this, we do a spurion analysis. So this is an explicit breaking. But what the outcome here is that if you want to get, so if you integrate out those heavy fermions, you can basically just look at the spurion charges you get for the tops, and then depending on which representation of the top partners I'm coupling to, I get several different possibilities for the spurion charge of my top mass. So the upshot is I can relate the couplings of the pseudoscalar to the tops to the top mass. And there are several possibilities which depend on which top partner my elementary top is dominantly mixing with. So this gives you another discrete set of possibilities. And now to the final complication. How do we get mass? How do we get mass for the pNGBs? We can, in principle, so there are 3 potential sources. One is you now have the A and you have the eta prime. One is a chi-chi, one is a psi-psi. bound state. You can give underlying masses to either of them. To the psi-psi, you actually don't want to give an underlying mass because this would boost the mass of your Higgs up as well. But you also have a global anomaly because, so you have the chi-chi and the psi-psi condensate, and they also couple to my confining group. But one linear combination is massless. And the orthogonal linear combination gets the mass from there. But if you look in detail, then you now get a mass contribution from this anomalous mass, but you also get a mass contribution from the underlying fermion mass. So those two mix, and you get a mixing angle which depends on the anomaly mass, which you can determine on the, in principle, on the lattice. The mass you give to your underlying fermions is an explicit external perturbation. So this you can't determine on the lattice, but you can use as a control parameter. And those two things play into the mixing angle of those states. So in the end, you get one mass or one very light mass eigenstate A, and then one mass eigenstate which we assume to be heavy. Here I'm opening a parenthesis. In QCD, the eta prime is getting heavy, but if you go to SUN theories, then actually your eta prime is getting light, although it is anomalous. So we leave the mass of the mass you get from the anomaly here as a parameter.
Is that just a factor of the number of follows? A factor of the number of follows, or?
I think so. This is something I'm taking from the literature. It was something we were originally, or I was originally not aware of, and we were always thinking that this state is being heavy. But then I think Francesco Sannino was at least pointing out to me, I think Giacomo and Gabriele knew about this, that in large N theories, the eta prime is getting light, so it's premature to make the assumption that one state is heavy and decoupled. One should leave it in the game, and so we are leaving it in the game. Other important point is that this mixing factor here depends on the values for your decay constants. Now, as you have the mixing, so your mass eigenstate is now a linear combination of the psi-psi and the chi-chi final state. One of them has a color charge, the other one has an SU2 charge. So now as you mix, this state couples to gluons as well as to the full electroweak group. So it's this mixing really which gives you the coupling to all three parts. The non-abelian gauge, the non-abelian pNGBs either have either SU2 and U1Y charge, or they have SU3 and U1Y charge. But you don't get couplings for both.
Can you just expand a little bit on the incidental contributions? How do you get those?
On the mixing contributions?
No, the instant. So capital M sub A.
Yeah.
Can you expand on where the capital M sub A comes from?
Oh, this is just to say that we have one linear combination which is anomaly free.
No, just the origin of MA. Where does it come from? It's generated by incident effects.
Yes.
So what incident effects are you talking about? Incident from where? No, from what group?
So all I'm saying here is that this linear combination is anomalous. So it will pick up a mass from the anomaly of this linear combination with my confining group. Or it can pick up a mass combination from that. And originally we were assuming in QCD, you get a mass contribution there which is of the order of lambda QCD.
Here is lambda, whatever, this mutation.
The naive expectation is that it would be lambda hypercolor. But I don't know whether this is the case for every gauge group, and I don't know whether it's generally known that it is. And as said, Francesco was pointing out that for QCD in the large NC limit, this mass is going down. So you get or you can get a mass contribution here, but the precise value of the mass is something which needs to be determined from the strongly coupled theory. And this slide you know again. So now we have all the ingredients to write down the effective Lagrangian, and yeah. So the mass I was talking about. So those states A and eta prime are now the mass eigenstate of this mass matrix. And if you look into detail into the expression for those coefficients kappa G or kappa B, you know the anomaly coefficients for the psi and the chi state. So you know the anomaly combination for the mass eigenstate. But what goes into this is the two anomaly coefficients plus the mixing angle, which depends on the decay constants or their ratio. So in that sense, you can calculate those couplings, but there are uncertainties which come from that we only have an estimate and not a precise number for the ratio of the decay constants. We don't have a precise number for the heavy mass which goes into the mass diagonalization from the anomaly. So in that sense, you can calculate them in principle, and we take limiting values here. But in practice, if you want to fully nail down the value, you have to determine those decay constants. Similarly, couplings for the top, and you can do the analogous spurion analysis also for light quarks. So this determines you the couplings of the pseudoscalar to fermions. The reason why this is proportional to MF here is also this is a pNGB, so it's a derivative interaction, and if I have a derivative here and I just pull it over on my fermions, this is precisely what's giving me the proportionality to the mass here. This F, yes, okay, and then you can calculate those contributions of Higgs to pNGB couplings, which are induced, and they are loop induced. I have a slide on this later, but I think I won't go into this a lot. So in that sense, you can calculate the couplings here. West-Sumino-Witten. So what we do here is we calculate the anomaly coefficients. Just ignore the WZW. Let me call it anomaly coefficients. Yeah, it's just a calculation of the anomaly there. This is so you can go through all the models and then calculate all those coefficients, and this is just a table from the paper where we did that. And here are also the values for the ratios of the different decay constants we assumed, and the resulting values of the decay constant you get for the mass eigenstates A and sorry, this should not. No, this should be psi. This is the ratio of the decay constant of the mass eigenstate to the decay constant you get for the psi bound state. This is just to say you can calculate those numbers, and those numbers are typically order 1, apart from very few exceptions in some models where they can get larger. And you can do a similar thing for the couplings to the top and the couplings to the fermion of the A and the eta.
So what are the input values? What are the free parameters in the end that you're fixing in order to get these numbers?
So apart from the assumptions we made here is that we assume that the mass you get from the anomaly is large, so it's kind of a decoupling limit. And we assumed that the decay those decay constants, that you have the large n relations between the decay constants. That's all.
Yeah, but they have to put some values somewhere, right? They have to put some values, some numbers in order to get those numbers there.
No, those are all group theoretic coefficients, basically.
Really?
Yes. See. Here you get the anomaly coefficients, and those just come from the dimensions of the representation. The ratios of, or the limits for f are just determined by the dimension of the representation. And if I go to the expression for the mixing angle, in here I have the charges of my, so I have my decay constants, and
Constants you have to put in, right? Decay constants you have to put in. They're not given by group theoretical factors.
I have one decay, or I have one gauge group confining, and now I get 4 decay constants, but I make assumptions about the relations of the non-abelian and the abelian part, which only depend on the dimension of the representation. And I make assumptions about the relations of the two non-abelian parts, and they also just depend on the representations.
The ratios only depend.
Exactly. So I have one overall scale f, and so in the end, the only free parameters for a given model is this parameter f psi, and the mass here. Because if I just take the contribution from the anomaly, then the anomaly-free combination has 0 mass. So in order to give that a mass as well, we give a mass to the underlying fermion, but this is an external breaking, which I can't calculate from the strongly coupled sector. So this is a freely dialable parameter as well, which is protected against radiative corrections, but which is an input parameter. And then all the other coefficients with the assumptions made are fixed and just those, and they just come from group theoretic factors. And similar for the couplings to the top and to the fermions, there are different cases depending on which top partner I couple to strongest, so those are basically the spurion charges for the psi and the chi. So there are different cases, but I can determine those factors. But each number has an implicit theory error bar, which comes from how well those relations between the underlying decay constants are realized.
Do you have a test of those ratios in some lattice for some cases? Does anybody ever took a big group and really...
There are first groups doing lattice simulations. So the problem is, let me go to the list of models. The problem is, if you look at the gauge groups, those are SO, SP gauge groups. There are very few SU gauge groups. So most of the lattice results are SU3 or SUN or SU large N. There are first groups doing simulations on SP2N. And I would have to look whether they also have a determination of the decay constants. So I have to look it up. I don't know whether results are there yet. Also, this is for a relatively complicated construction with two sets of underlying fermions. Good. So this was basically how you arrive at the Lagrangian and at all those couplings and the underlying assumptions going into it. And I'm already out of time. So I don't know whether you want to see any of the phenomenology, how much time we have. You saw some results yesterday.
So the lightest states are these A and eta?
So the lightest states are A and eta are standard model singlets, so they don't pick up any contributions from standard model gauge loops. For the colored pNGBs, you get contributions from QCD.
They're not too large, right?
No, we did a naive estimate by just writing out the operator expansion for those in a paper 4 or 5 years ago. So this is giving you a substantial contribution to the mass.
So we can just say what is the most.
So the lightest state you would expect.
Way to look for this model. The best way to look for the model. And probably it's not the lightest state because the singlet maybe can pair produce the color octets. I don't know. So which
Yes. So the best and simplest way to look for this model. Wait, now I have to go to the pNGB list. I would say you can look for the color sector. The octet is present in every models, and this.
Actually single produced, right? By global fusion. Can you do that?
You can do that, but this is a state which only couples through an anomaly term. So it's a very small coupling. And you also get couplings to TT bar. Actually, if you want to see more about this, there I have a pheno analysis for the color octet. What I have in terms of pheno analysis is I showed you the results for the color singlet yesterday. I have an analysis for the color octet, purely bounds, and then there was the analysis for vector-like quarks decaying to the singlet, and then also an analysis for exotically charged 5/3 charge top partner with all possible decay channels, because there are many more than you have under the minimal assumptions. And we did an analysis to see whether the bounds change if you have different decay channels there. Those are the 4 analyses I have in. If you want, I'll show you quickly some results from the. Two slides. Two slides, so this is all, sorry, 3 slides. Color octet. What we use as an input is the mass for the color octet, and then you have couplings to TT bar, and you have those anomaly couplings, which give you couplings to glue, and to glue U1Y, meaning a coupling to glue photon and a coupling to glue Z. As you couple to the U1Y here, the branching ratios of glue to glue photon to glue Z is fixed. And they only depend on the charges of the underlying fermions. And there in the different models, you have 2 cases, either the hypercharge is 1/3 or 2/3. And in particular, in the 2/3 case, you get a branching ratio, or you get branching ratios here to glue photon or glue Z of 1 to 0.2 to 0.06. So you get a large branching ratio into glue photon, actually. The branching ratio to the top is a different story, and we leave the relative branching to gauge bosons and to the top as a free parameter. And now you can go into the phenomenology, and you can look for pair production. So now you have 2 octets pair produced via QCD, and they can decay into all combinations, but the only searches which are available are searches for 4 tops in the final state, or there is a CMS search for 2 particles which both decay into 2 jets. So it's a 2 dijet search. The bounds you get from those we were extracting from the papers, and now if you take the QCD pair production cross-section here as a function of mass, this we know, this is fixed. So now you can determine the bounds as a function of the branching ratio of the decays into TT bar versus the decays into jets. And this is what you find here. Here you have this ratio of the couplings, which is parameterizing the branching ratio. And here you have the bounds in terms of the mass of the color octet. So
there's no search for gamma gamma jet jet, which would be nice.
You start to worry me, because this is precisely the paper we are currently writing. So there is currently no search like this. You can also go for single production, and here we have the production cross-section for 1 reference value, and for this reference value, this is now model dependent because it comes from the color octet to glue coupling. So we fixed this value to a reference value to plot this line, but from the tables beforehand, you can calculate the cross-section for each model. Here there are searches for jet-jet, for TT bar, and there are searches for what is called excited quarks. So they look for gamma jet. So we have all of those. And here now, whether depending on whether for the 2 cases of underlying hypercharges, you get 2 plots where what is in dark blue is excluded by pair production. And what we put here into the different colors are areas where currently the TT bar bound is strongest, the glue bound is strongest, or the glue photon bound is strongest. So you see that glue and glue photon compete here for single production. You have all the searches, but for pair production, there is nothing looking for pair production and decay to glue photon. And this is something we are currently finalizing because, yes, for those models, if you take 1 or both of the fermions decay into glue photon, you have a much smaller background. So you can use this in order to constrain those models better. And I should probably stop here, and the other pheno examples are in the slides, and some of them you have seen yesterday already. Sorry for overrunning so much.
Is the amount of people working in this stable, going up or going down? What's the, so you can build models, but
okay, I give my take, or Mariano, or Thomas. My take is that, okay, the extension of standard model, we're looking for extension of standard model to understand the hierarchy problem, right? So there's supersymmetry, one possibility, there's composite Higgs, another possibility, composite models.
Right, but the directions are not changing. The directions are essentially waiting for this some new.
I would say that supersymmetry is going down. Maybe Mariano.
Yeah.
And the composite Higgs had a peak, but now it's stable going down. So.
I mean, as long as there are no experimental results, everything should go down at the long range.
Let's say.
The only thing you can say is going up now is neutrino
Okay, but I'm asking about hierarchy. About the hierarchy in people, there's no people are ruling out models using LHC or they are.
Did you go to the colloquium with Mariano? He probably talked about hierarchy problem a lot. Yeah, of course. So you probably remember what Mariano said about the hierarchy problem.
Okay, so there's no. So this is essentially the newest direction that's coming.
Can we take the following part of the video because I don't want to insult anybody.
Okay,
but
we can turn this off.
Okay.